So here we continue chapter 2 on the chemistry that we need for understanding biology. And we've already covered topics including what matter is, elements, atoms, and importantly, different kinds of chemical bonds. What we're left with is discussing water and the importance of water to life, and in particular, properties and characteristics of water that are unusual compared to other kinds of molecules, and how those properties and characteristics are absolutely necessary for life as we know it. So we're starting off on this slide by just making the point that we live on a water planet. When you look at this image taken from space of our Earth, and see just how much of our planet is covered by water. 75% of Earth is covered with water. And we see water everywhere in the atmosphere as water vapor, locked up high in the mountains or at the poles in the form of ice, solid water. Water is everywhere. And of course, life as we know it is mostly water. Your body is mostly water. So we can't leave the topic of chemistry and move on into topics in biology without understanding some of the unique things about water. And the last point I'm going to make here goes along with the last bullet on this slide, is that the structure of water molecules leads to emergent properties that are essential to life. So remember what emergent properties means. It means that when things are put together, when smaller parts are put together in a certain way to make a bigger system, that new characteristics come about, new properties emerge that don't exist at the lower levels. And that happens even with the little tiny water molecules. The photo I have on the bottom of the slide of some elegant whooper swans floating around in a winter lake, again, is just pointing out that water is everywhere. Water is what makes up our planet. These geese are living in an aquatic environment. They're surrounded by water vapor, the steam coming off, solid water, and of course their bodies are made of water. They rely on water just like we do. So let's take a look at these properties. So we need to begin by reviewing the structure of water molecules. First and foremost, they are polar. So remember what that means and why they are that way. They are that way because every water molecule is made of an oxygen and two hydrogens. And those oxygen atoms are very electronegative. They are pulling on electrons from the hydrogens really strongly, and the hydrogens are much weaker, so they're not pulling on those shared electrons so much. So that makes the oxygen atom a little bit negative. You can see the delta negative signs over the oxygens, and it makes the hydrogens a little bit positive. And voila, we have polar molecules. Now, polar molecules stick together. They stick together with those bonds that we call hydrogen bonds, which you can see in the figure here on the slide. How do you tell hydrogen bonds from covalent bonds in the figure? The covalent bonds are shown with solid lines, and the hydrogen bonds with little dots in between the molecules. And you can see the dots are extending from the slightly positive hydrogens in one molecule to the slightly negative oxygens in a nearby other molecule. Now, every water molecule can form up to 4 hydrogen bonds with other water molecules around it. So there's actually a lot of hydrogen bonds that are forming between water molecules, lots of little temporary attachments. Another thing that contributes to water's properties is the shape of the molecule. It's kind of V-shaped. So that's also important. So now these water molecules stick together for only a few trillionths of a second, and then those hydrogen bonds break, and the water molecule forms a hydrogen bond with another molecule. So it's very dynamic. They're constantly in motion, making and breaking these hydrogen bonds. There are 5 unique properties of water that are textbook lists, and I have outlined them here. So this is our starting point to investigate the properties of water and how they're important to life, is just simply listing these properties. So get started with memorizing them, learning them, and we will proceed in the next slides to discuss them one by one to help you understand them, the properties, and how they're important. But just to quickly go through, the first one listed is heat storage. Water changes temperature very slowly. It holds temperature very well. That has to do with what's called specific heat or heat capacity. And water is a champion at that. Another important property is ice formation, that when water turns into a solid, it floats, it doesn't sink. A third property is water's high heat of vaporization. The heat of vaporization is the amount of heat energy it takes to turn a liquid into gas. And as it turns out, water, compared to other substances, takes an enormous amount of heat to turn it into gas. And the reason why this is important is evaporating water molecules help to cool surfaces. They help to cool living things off. The fourth property here, cohesion and adhesion. Water molecules are polar, and so they stick to each other. That's called cohesion. Water molecules are polar, and so they stick to other kinds of molecules that are polar. That's called adhesion. And then finally, the polarity of water molecules causes solutes to dissolve. It says solvents here, but it should say solutes to dissolve. Solutes are the chemicals that mix with a liquid, and because of water's polarity, it really enhances and helps polar molecules and ions to dissolve. So we say water is the solvent of life. So I'm going to go through these properties now one by one and dissect them, and hopefully you'll understand a little bit better. So the first one, water property number 1, heat storage. So what is heat? Heat is a collection of matter's total kinetic energy due to the motion of molecules. All right, so there's a lot there in that statement. Remember, matter is anything that takes up space, has mass. You represent matter, air, atmosphere. The molecules in the air represent matter. So all of matter can absorb energy from the environment, and when that matter has kinetic energy, it's moving around, it has motion. That motion is heat. That's heat energy. And the amount of heat that is present depends on volume. So take a look at the figure that I have in the upper right-hand corner of the slide, pointing out to you, look, if you have a bucket of water and you have a cup of water, and they each start off at 25 degrees Celsius. So same condition, same temperature. And if you add exactly the same amount of heat to each body of water, the bucket and the cup, 50,000 joules, well, you'll end up with a warm bucket of water, and you'll end up with a very hot cup of water. So again, the point there is depends on the volume. The bucket has a much greater volume than the cup. So when you're transferring that equivalent amount of heat to each one, it makes a bigger difference to the smaller object, much less of a difference to the bigger object. Now, what's temperature? Let's take a look at temperature. Temperature is not the same thing as heat. Temperature is the average kinetic energy. It's not the total, it's the average kinetic energy of molecules. and it is volume independent. So what I mean by that is you could take a thermometer and stick it in the ocean, and you could take that same thermometer and stick it in a cup of water, and you could have exactly the same temperature, say 25 degrees Celsius, identical temperature. That just simply means that in that ocean and in that cup of water, the molecules of water are moving on average with the same amount of energy or speed. That's temperature. Again, going back to heat, the amount of heat, the total energy in the ocean versus the total energy in a cup is astronomically different. But temperature is not total. Temperature is average. So you can have the same temperature in a giant body of water or a small body of water. Now, water absorbs or releases large amounts of heat with just slight temperature changes. Why is that? How come? Because there is a huge difference in the specific heat between water and other substances. And let's take a look at that. Oh, by the way, the figure I've got in the bottom right-hand corner is kind of touching on this subject. The heat capacity, or the specific heat of air, versus the heat capacity or the specific heat of water is entirely different. So you can see by that graphic the total amount of heat that is trapped in our world's oceans compared to the amount of heat that's trapped in our air is astronomically different. The ocean's going to change temperature much more slowly than our atmosphere is. And we see that and live by that day in and day out. So we're still on this property number 1 of heat storage, and here I am discussing specific heat, a little more detail to relate what it is and how it is important to this property of water, of heat storage. So what is specific heat? Specific heat is the amount of heat energy that's needed to change 1 gram of a substance by 1 degree Celsius. So that's a very specific definition. In chemistry and physics, that's what it is. So you can see in the table that I inserted in the top of the slide that water has a specific heat of 1. That means it takes 1 calorie of energy to change 1 gram of water by 1 degree Celsius. You can see in comparison, ethyl alcohol, which is the alcohol that's in a beer or wine, is 0.6. It takes 0.6 calories to do the same thing. Aluminum, 0.2. Iron, gold, really low. So these are just a couple comparisons, but trust me, water compared to other substances has a very high specific heat. And why is that? The second bullet here answers this. It has a high specific heat. It takes a lot of energy to raise or lower the temperature because of the hydrogen bonds. It takes energy to break the hydrogen bonds and get the water molecules moving faster. And remember, that's what temperature is. Temperature is a measure of the average kinetic energy. So because it takes so much energy to break those hydrogen bonds and get the molecules moving faster with more kinetic energy, that's why it changes water, changes temperature so slowly. That's why it stores or holds heat so well. So the bottom line here, why is this important to life? It's important to life because bodies of water change temperature slowly. So that means our oceans, our lakes, remember, planet Earth is mostly water. We are a water planet. So we change temperature very, very slowly. And this protects living things. It protects the living things that are living in these bodies of water from drastic temperature changes. We are made up mostly of water. So it protects our bodies from drastic temperature changes. And even nearby land areas that are close to large bodies of water, they don't change temperature very quickly. So all around, this property of high specific heat of water is protecting life from drastic temperature changes. All right, let's move on to water property number 2. Ice floats. That's what your textbook says. Well, no, actually, that's not what your textbook says. That's what I'm saying. Ice floats. I like that as a better pronunciation or pronouncement of the property of water. So most substances have a higher density as a solid compared to a liquid. That is, with most chemical substances, when they go from a liquid to a solid, the solid, because the molecules are closer together, they are packed closer together. That's what makes them more dense. And the more dense that something is, or that means that it'll sink compared to a liquid. If a solid is more dense than a liquid, then the solid's going to sink. If a solid is less dense than a liquid, it's going to float. You can think about wood. We all know wood floats. Why does it float? Because the density of the molecules that make up wood is less than the density of water. So it floats on top of the water. So now as water cools, like other substances, the molecules get closer together because they have less energy. And because they have less energy, they're not moving as fast, they're not moving as dramatically, and so they're basically closing in on each other and the water's getting more dense. And water has a maximum density at 4 degrees Celsius. Freezing is 0 degrees Celsius. So water actually has its maximum density when it's still liquid. And as the water slowly approaches the 0 degree mark to turn to solid, the molecules of water actually start spreading out more, distancing from each other more. And they lock together into a lattice, kind of a honeycomb formation as the ice forms. And you can see that especially in the figure that's in the bottom of the slide. Take a look at that closely. In the liquid water on the right, molecules are close together. They've got their hydrogen bonds forming and breaking, and the molecules are moving all around. But when ice forms, the molecules spread apart. They are less dense. There's more airspace between them. And as a result, the solid form floats. What's the importance to life? The importance to life is that when ice forms on the top of bodies of water, like lakes and oceans, it forms an insulating barrier, like a blanket, that protects the life below. If this didn't happen, bodies of water like our oceans and our lakes would freeze from the bottom up, and life would be destroyed. It would be killed. So because it happens the opposite from that, ice floats, life is protected. Of course, global warming is threatening this balance because many of our oceans and so on and glaciers are melting. So the dynamics of this is changing on planet Earth. Let's move on to property number 3, high heat of vaporization. I'll stick my face right in the bottom middle there. It takes a large amount of energy to vaporize liquid water, to turn it from a liquid into a gas. Like think about putting water in a pot on the stove. You've got the liquid in the pot, and eventually, when you turn up the stove, you'll start seeing steam come off. That's the vapor. And you know as well as I do, it takes a long time, a lot of heat to completely boil off that water and turn it to vapor. That's because of water's high heat of vaporization. And once again, it has to do with the hydrogen bonds. These properties keep coming back to water's polar properties and how the water molecules form hydrogen bonds. So the hydrogen bonds are holding the water molecules together. They're like little pieces of Velcro. As a matter of fact, it takes 580 calories That's a lot of energy to evaporate or vaporize 1 gram of water at 25 degrees Celsius. So if you start off at 25 degrees Celsius, you just have a gram of water, which is not very much. It'll take 580 calories to totally evaporate that water. So when water does vaporize, when it turns to gas, it takes heat energy away. That is, the molecules that have the most energy, they're the ones that break free. They're the ones that leave the liquid state and shoot out into the atmosphere as a gas. When those fastest moving molecules leave, when the molecules with the most energy leave, it leaves behind on average molecules that are moving more slowly. This translates to a lower temperature. Because remember, temperature is the average kinetic energy. So if the fastest, most energy-rich molecules are blasting away from the water's surface and leaving behind slower ones, that literally translates to a lower temperature. What's the importance to life? Evaporative cooling. When water evaporates from the surface of any object, but we're talking here about living things, animals, plants, when it evaporates, it takes energy away, and the living thing is left a little bit more cool. So you see in the photo in the upper right, there's a, what is that? Mine's blanking out. Boxer. Looks like a boxer. And of course, dogs pant to cool themselves off. They've got huge tongues. They stick their tongue out. And as the water evaporates from their tongues are full of blood. The blood's bringing heat to their tongue. The heat in their blood is heating up the water on their tongue and, cools them off. In a similar way, you can see the elephant spraying water on its big flappy ears. Again, the blood being delivered to the ears is bringing heat to the ears. That heat is transferred to the water on their ears. The water evaporates. The elephant is cooler. We sweat. So we release water onto the surface of our body when we begin to overheat, and we have that adaptation specifically to help us cool off. By the way, I didn't mention the figure on the bottom of the slide, but I pulled that off the internet. It looks kind of complex, but the bottom line is just showing you how much heat energy it takes to turn water into vapor or steam. So if you look carefully, that's what it's showing you. So high heat of vaporization helps to protect living things by cooling them off. And here we are at property number 4, cohesion and adhesion. So these properties are really important for water sticking to itself and water sticking to other things. So here it's important for you to know these definitions. These are definitions that will come back to you as you pursue biology in different contexts. Cohesion. Cohesion is a physical phenomenon that occurs when molecules stick together. Molecules of the same type, exactly the same type. They stick together due to hydrogen bonds. So because water's polar, that makes it cohesive. It's just a word that we're using that describes that property of sticking to yourself. So you can see that in the top right photograph where there's beautiful little droplets of water hanging like grapes from a spider web. So the fact that all those water molecules are sticking to each other, sticking to themselves and forming those droplets, that's what allows them to form those droplets, those beads. Now on the bottom right, there's a picture of some insects, some water striders that live on the surface of the water. And you look carefully at their legs. You can see that the legs are resting on top of the water. They're not puncturing the water, but they're literally resting on top, just like your feet rest on top of a floor or the ground. The animal is not breaking through the surface of the water because the water has what's called a high surface tension. The molecules of water on the top film, the top surface of the water, are sticking to each other and forming like a protective covering that's hard to break through. If the legs of those insects literally broke through that surface tension, then the insect would probably sink to the bottom, just like we would when we break the surface tension of the water. We're a heavy organism. You could take by the way, you could take a paper clip, which is metal, of course, take a metal paper clip, and you could actually rest it on the surface of water and it'll float. It's kind of counterintuitive because the metal is more dense than the water, so it would sink if it penetrated the surface tension. Of course, if you drop the paper clip on the water into a glass of water, it would break the surface tension as it's falling, and it would sink. But if you gently rest it on the surface of the water, it is possible to do this. You can get it to float. Now, adhesion is a property that occurs when different types of charged particles stick together, like different kinds of molecules that are all polar. So, for example, look at the top photograph. Again, those droplets of water that are forming because of cohesion, they are sticking to the spider web. So that means the spider web and the water are adhesive. They stick to each other. Glue, of course, is an adhesive. It has chemical properties that sticks to other surfaces like paper, and they can stick together. So these two properties, cohesion and adhesion, are both having to do, again, with water's polarity. And here we are at property number 5. Polarity dissolves solutes. Water and ionic solutes, polar and ionic solutes easily dissolve in liquid water, producing a solution. Let me go over that first statement. A solvent is any liquid in which other chemicals can dissolve. So water is a solvent because there are lots of chemicals that can dissolve in it. The chemicals that are doing the dissolving, the chemicals that are mixing in the liquid and kind of disappearing, those are called solutes. We call them solutes. When you mix solutes with a solvent, you get a solution. You can imagine taking a glass of water in your kitchen and sprinkling some salt in there. The water is the solvent, the salt is a solute. Take some sugar, mix it in there with a spoon. The sugar is also a solute. Take some paprika, sprinkle it in there. If it can dissolve in the water, then it also becomes a solute, and you're making a solution. Now, this property that water has of being such a great solvent to dissolve things, that helps life because it helps bring molecules and chemicals together within our cells, and it helps or facilitates chemical reactions. So that's kind of the big picture. That's the importance to life, is that water helps to dissolve chemicals, bringing them together for the chemistry of life. Now, let's go over what it means to be hydrophilic or hydrophobic. Hydrophilic. Hydro means water. Philic means loving. So if something's hydrophilic, it means it's attracted to water. What's attracted to water? Ions, anions that are negative, cations that are positive, they're attracted to water, so they're hydrophilic. And polar molecules, like sugar, they are hydrophilic. They're attracted to water. They're attracted because of opposite charges. The negative oxygen in a water molecule is going to be attracted to, say, positive ions, like sodium and salt, or the positive part of a sugar molecule, etc. Now, what ends up happening is water molecules surround, kind of gang up and surround these charged particles, and they form what's called a hydration shell, a sphere of water that's surrounding these little particles and separating them and making them dissolve. Take a look at the figure in the upper right. It's showing you what happens if you put some salt into water. The water molecules are going to surround the chloride ions in a hydration shell. They're also going to surround the sodium ions in hydration shells. And even look at the orientation of the water molecules in the picture. The positive hydrogens in the water are closer to the negative chlorides, and the negative oxygens in water are closer to the positive sodiums. Everything is doing what we would expect in terms of opposite charges. Now, what are hydrophobic solutes? Phobia is fear. So things that are hydrophobic do not dissolve in water. Why not? Because they don't have any charge. They are non-polar. So water molecules will stick together with each other because they're polar, but non-polar molecules will be kept away. They won't have any attraction to the water. So basically the water's like, I don't want to have anything to do with you. You're not charged. Take a look at the bottom figure I have on the slide, the beaker that has water in it, and it shows you the hydrogen bonds between the water molecules. And then there's some oil on top, like say vegetable oil. Well, oil is non-polar. It's made up of carbons and hydrogens that are sharing electrons pretty equally. And so those covalent bonds are non-polar. And as a result, the oil molecules have no charge. So the water molecules don't want to have anything to do with them. So the waters stick to each other and the oils stay separate. They are hydrophobic. So the overall bottom line here is that water, because of its polarity, dissolves a lot of different kinds of charged substances, and we call those charged substances hydrophilic. And this helps to allow life to exist by bringing all these chemicals together that need to interact for the chemistry of life. All right, well, now we're in the last section of this chapter, section 2.5, and it's titled Water Ionizes. What it's mostly about is the subject of pH. What is pH and how is it important to life? Water ionizes. So, occasionally, a hydrogen atom that's participating in a hydrogen bond between two water molecules. Take a look at the figure. It leaves its parent molecule, its parent water molecule, and it leaves as a hydrogen ion, which means that it leaves its electron behind and only the proton leaves. And that hydrogen ion, that proton that leaves one water molecule, attaches to another water molecule. And that results in what's called a hydronium ion, a water molecule that has a hydrogen ion stuck to it. That's H3O+. Typically, we just represent that as an H+, as a hydrogen ion. But in fact, there aren't any free-floating hydrogen ions in water. As I mentioned here, they're actually stuck to other water molecules. So there's a very small percentage of water molecules at any one moment that are doing this, but still, there is a fixed percentage. In pure water, the concentrations of these hydronium ions, or we'll just call them hydrogen ions for short, and hydroxide ions, those are the OH minuses, they're exactly equal. And although they're in very low concentrations, these ions are extremely reactive because of their charge. And if they can change the structure of molecules like proteins and DNA, and that could kill living things. So the reason why we're talking about this is because ionized water molecules, hydrogen ions and hydroxide ions, can change the shapes and functions of molecules, and this can be very dangerous to life. So let's look at this in a little more detail in terms of the pH scale. So those two letters, pH, it's not on the slide, I'm thinking I'll tell you right off the bat, stands for potential hydrogen. That's what pH stands for. And the amount of ionized hydrogen, that is the H pluses, the hydrogen ions, the amount of ionized hydrogen from water in a solution can be measured as what we call pH, potential hydrogen. So it's a measure of the amount of those hydrogen ions. Because, as I said, we want to do that because these ions are very reactive to molecules and living things. Now, on the right-hand side of the slide, I've taken the figure from your textbook showing the pH scale. And the pH scale is logarithmic. I don't know how much math you've had or if you've covered logarithms in math or understand much about that. But nonetheless, the calculation of pH is a logarithmic relationship. So you can see the formula I put there. It's the negative base 10 logarithm of the hydrogen ion concentration. Now don't worry about that formula very much. I'm not going to ask you to use it or do any math with it, but here's the big deal about it. This is what you need to know, is that because the pH scale has this logarithmic component, that means for every 1 unit of change in the pH scale, the hydrogen ion concentration, the amount of hydrogen ions, changes by 10 times. That's what it means. So if something, say, starts off at pH 7 and it goes up to pH 8, okay, that's 1 pH unit, but that means the hydrogen ion concentration has changed 10 times. If it goes from 7 to 9 in the pH scale, that means it changes 100 times. That's 2 pH units. So that's 10 times 10. Okay? Now, another thing is describing the pH of solutions. We use the terms acidic, neutral, and basic. If a solution has a pH of 7, that means that there's an exactly equal number of hydrogen ions and hydroxide ions, 50-50 mixture, and we call that pH neutral. If a pH is less than 7, then we describe it as acidic. And by the way, if it's less than 7, that means the hydrogen ion concentration is higher than the hydroxides. And the closer that the pH gets to 0, so the pH number is going down, the more and more hydrogen ions there are. Look at the pH scale figure. You can see at pH 7, that would be like pure water. Our blood is pretty close to that. If you go down to pH 6, that's slightly acidic. Our urine is about that. Our saliva is about that. And then go down through the pH scale. You can see pH 2 is stomach acid, lemon juice. That's why it hurts and burns so badly if you throw up or vomit, because that stomach acid has a pH like lemon juice and it burns the tissues in your throat and in your mouth. Anyway, if you go higher than pH 7, now we describe those solutions as basic. And now the hydrogen ion concentration is less than the hydroxides. So if you look back at that scale, you can see seawater is slightly basic, pH of 8. You can see oven cleaner has got a pH of 13. It is very basic and it's very corrosive. So pH scale measures the concentration of hydrogen ions compared to hydroxides. The numbers range from 0 to 14. Every change in the pH scale by 1 unit is actually a change 10 times of these ion concentrations. And that is the big stuff you need to know off of this slide. So what is an acid? What is a base? How does that figure into this pH business? So an acid is any chemical substance that donates or increases hydrogen ions. That's an acid, period. And hydrochloric acid, HCl, is considered a very strong acid. That's because all of the hydrogen ions are dissociated and free in hydrochloric acid, And so if you add any hydrochloric acid to any solution, it's a very strong donator of hydrogen ions. On the other side of the coin, a base is any substance that reduces hydrogen ions. So I have two examples here. Ammonia is NH3, that's its formula, and hydrogen ions attach to ammonia. They stick to ammonia. So ammonia is a base because it removes hydrogen ions. Sodium hydroxide, NaOH, that's a strong base. It is made up of hydroxide ions. So if you add those hydroxide ions to a solution, then you are counteracting the hydrogen ions that are in there and proportionally changing their concentration. So sodium hydroxide is also a base and will reduce the concentration of hydrogen ions. On the bottom of the slide, I've got carbonic acid. That's considered a weak acid, not a strong acid, because only about 1% of the carbonic acid molecules dissociate or break apart at any one moment. So that's a weak one, whereas hydrochloric acid is a strong one. If you look at the figure I've got on the right-hand side of the slide, it's just showing you, okay, if you start off with a neutral pH where the hydrogen ions are equal to the hydroxides, and you add an acid, like a couple drops of hydrochloric acid, HCl, then the hydrogen ions are going to go up, and your solution will become more acidic. If, on the other hand, you add a base, like, say, sodium hydroxide, then you're donating hydroxide ions, and that's going to make the solution more basic. So a little schematic there to give you a visual of how an acid or a base will change the pH. So here we are on the topic of buffers. Also has to do with pH. And I'll tell you right off the bat what a buffer is. It's a little bit farther down on the slide. It's any chemical substance that minimizes the changes in hydrogen and hydroxide ion concentrations. Translating that, buffers help to keep pH stable. Now, the internal pH of most cells, the cells in your body, a bacterial cell, an amoeba, is pretty close to 7. It's pretty close to neutral. Our blood pH, by the way, is 7.4. So is that basic or acidic? Slightly basic. Even a slight change in pH can be deadly. So for example, if your blood pH, for some chemical reason, drops to 7 from 7.4, or goes up to 7.8, you'll be dead within minutes. So it's absolutely critical that your blood pH remain pretty stable, around 7.4. What's the solution to this? How do we solve the problem and make sure that our blood pH doesn't go up or down too much and kill us? Well, our blood contains chemical buffers, chemicals that help to prevent the pH from shifting. One of the big important buffers in our blood is carbonic acid, H2CO3. There are other buffers as well, but this is a very important one. Now look at this chemical equation. H2CO3, and then follow the blue arrow to the right, breaks apart into HCO3, which is a bicarbonate ion, and a hydrogen ion. But then look at the blue arrow going to the left. That is telling you that the HCO3 and the H can combine together and make carbonic acid. So this chemical equation can go both ways, right or left. Now here's how it works. If your blood pH begins to drop, that means it's becoming more acidic. That means you have too many hydrogen ions. It's becoming too acidic. You need to remove those hydrogen ions. You need to take them out of your blood. So what direction would this chemical reaction go to remove hydrogen ions and bring your pH back up to 7.4? The reaction would move to the left. You would take some of the bicarbonate ions and the hydrogen ions and bond them together and make carbonic acid. That would remove hydrogen ions and counteract the pH drop. What if your blood pH started to go higher than 7.4 to become more basic? Well, then we need to add hydrogen ions to your blood to counteract that and bring the pH back down. Take a look at that equation again. What direction of the equation would add hydrogen ions and bring the pH back down to 7.4? The reaction would have to move to the right. The carbonic acid would have to break apart and release hydrogen ions to bring that pH back down. So basically, if you're looking at this chemical equation, it's going to either move or shift a little bit to the right or to the left, depending on whether the pH needs to be brought down or brought up. And that's the way a chemical buffer works. And it helps to protect us and keep us from dying. So that's it for topics in Chapter 2 that you need to know about, that I want you to know about. And you should test your understanding of Chapter 2 in a variety of ways. One way is there are some review questions on page 48 of your textbook. So go into your e-text, see if you can answer those. There's a set of review questions in the Canvas module taken from the McGraw-Hill website. So that's a 10-point assignment. So do those as well. You have 2 chances to do that. Review your lecture notes, make some flashcards, test yourself with flashcards, answer the questions on the study guide in the Chapter 2 module. Make sure you can answer those kinds of questions without having to look at your notes. Have some study groups, of course, in various ways to quiz each other, help each other. But the bottom line at this point is you need to be quizzing yourself and testing yourself in a variety of ways to master this information. Oh, the one last thing, the self-tests. Those self-tests that you have access to with your password. There's a Chapter 2 self-test. There's an inorganic chemistry self-test that gives you practice with all the concepts covered in this chapter. So make use of all this to help you get ready for the next big lecture exam that will ask you questions about chemistry. That's it for now. I'll see you soon.